you're new, welcome. SFAA has these lectures online. We used to have them at the Randall Museum in San Francisco, but with COVID, it's been closed for up 9 months now. Well, 7 months, sorry. And then we hope to return there next year, but for now, we just do these online lectures. You can find our recordings of our lectures on YouTube and Facebook under the SFAA channels. This will be streamed live, and later on it will be available to watch anytime that you want. So yeah, I hope you have use it as a resource to inform yourself, to learn more about what's going on in astrophysics and planetary physics and geophysics. So Linda, do you want to tell us who we will be talking with us next month?
Okay, thank you very much. On December the 16th, goodness, I can't believe I'm saying December, but at any rate, why do galaxies die? How Silicon Valley's spectral revolution will solve a 100-year-old mystery. The speaker is Kevin Bundy, assistant astronomy professor, UC Santa Cruz. Over 100 years ago, Edwin Hubble noticed two distinct classes of galaxies, youthful spirals and smooth faded ellipticals that were red and dead. The MANGA survey, M-A-N-G-A survey, is mapping 10,000 nearby galaxies to help understand how all types of galaxies formed in the early universe. With the spectral revolution going on in Silicon Valley, nanotech and photonics will help transform astronomy instruments in the future. And then on January 20th, mapping the missing matter in our universe, Sunil Simha, UC Santa Cruz, Department of Astronomy. Fast radio bursts were discovered only in the last decade. They last a few milliseconds and are an extremely bright source of radio waves. FRBs have been detected by the Australian Square Kilometre Array Pathfinder and the Sloan Digital Sky Survey, and you will learn about this most recent work on FRBs, fast radio bursts.
Linda, sorry, I made a mistake. I forgot one thing.
Yes, sure.
So we have board elections starting tomorrow for the club. We have a slate that will be sent out in an email. Members will get a link to online voting where they can say yes or no on individual candidates or the slate. I'm not running for president next year. I'll be in the board. Anthony Marrero, who was secretary and also board member a few years back, he's joining us again. He will be running for secretary.
Great.
Then so the officers basically being shuffled around. Jessica will be president. Bill will be vice president. But basically, we're just shuffling the positions around since I would not be president next year.
Will Jim Burke still be on the board?
Oh yeah, Jim Burke will be.
I mean, well, he's treasurer.
He will be treasurer again.
Very good.
And then the board directors remain the same. I'll just be demoting myself to board director.
And if anyone's interested in running for the board, we could use a couple of alternates. So if anybody wants to step up, just email either the president or the treasurer or secretary, and we'd appreciate that.
Or email vice president.
Yeah. And then the position of board director or alternate doesn't have any responsibility other than attending meetings. We have a meeting every month, and they're all virtual, and they're we try to keep them to an hour. And they basically are to do with scheduling, making sure we have speakers, the Zoom, and we're discussing possible events for next year once hopefully the vaccines and treatments are available and we can go out more safely. And there's not a lot to discuss on the meeting, so they're pretty light. So don't be afraid of joining because of the board meeting. It's really just making sure the club keeps running, and that we have activities planned and crossing all our T's and I's, dotting our I's. And the real heavy job is the treasurer keeping all the memberships, and the president job is just signing paperwork. And you don't have to host this meeting just because you're president. That's something I chose for myself. I could have been any other board member. So basically that's it.
Okay.
Just keep an eye out for the email for members. Non-members, obviously, you will not receive an email and you won't be able to vote. But if you're interested in becoming a board member, you need to be a member of the club. And our website has all the details on that. Right, I'm gonna mute everybody just to make sure that nobody is. I'm gonna unmute you, Linda, just a second. I can't find Linda. There she is. So Linda, you need to unmute yourself again. Go back to.
Okay, all
okay,
right.
There you are.
I'm very pleased to introduce our speaker tonight. Eric Charles grew up in New Mexico. He received his PhD in high energy particle physics from the University of Wisconsin in 2002. After 3 years as a postdoctoral fellow at the Lawrence Berkeley National Lab, he moved to SLAC National Accelerator Lab in 2005 to help with the construction and testing of the Fermi Gamma-ray Space Telescope. And he stayed on as a member of the Fermi instrument team. He's been working to improve the performance of the telescope and is actively studying the data it gathers on the gamma-ray sky. His hobbies include metalworking and pyrotechnics. And now you know why tonight's lecture is called 12 Years of Cosmic Fireworks with the Space Telescope. A single gamma ray carries millions of times the energy of a single photon of visible light. The Fermi Telescope was launched in 2008 to measure these extreme events, and it has changed our understanding of the most violent objects in the universe. And very much we welcome Eric Charles. Thank you so much for being with us tonight.
Thank you so much for that lovely introduction, and thanks for inviting me for this. I'm very much looking forward to it. I'm going to go ahead and share my screen now and just get started with the talk. Since I can't see people raising their hand and stuff like that, it might be easiest if we save questions for the end. So anyway, okay, so here's my screen, and let me get this into slideshow mode. So hopefully that's in the nice slideshow mode.
Yes.
Okay. So this is a talk that's a bit of a reprise of a public lecture I gave a couple years ago at SLAC, at the lab I worked at, on the occasion of the 10th anniversary of the launch of the telescope that I've been working on for the last decade or more. And so I'm just going to go ahead and get started. Let's see. So on the outline of the talk, I'm going to say a few words about myself, and then I'm going to spend probably about the first third of the talk talking about gamma rays and how to make them, and gamma ray astronomy, why we do it, and then what the Fermi Telescope is, what the telescope that I actually work on is. And then the second half of the talk is basically going to be highlights, scientific highlights from the telescope. I'm going to sort of progress from talking about nearby objects to talking about some of the most distant objects that we observe in the universe. And that part of the talk is going to have a lot of animations. Fermi is a NASA mission, and NASA has just a really great public outreach group that does a really good job turning scientific ideas into very easy to grasp animations. The team that does that is excellent. And so they give us just a lot of really good material to work with. Okay, so I'll go ahead and get started. I think most of this was actually covered in the introduction. I grew up in New Mexico. I did both undergrad and graduate work in the Midwest, and then I did a PhD in particle physics. I was working on a project at CERN, the laboratory in Geneva, for a while, and then I came out to the Bay Area and worked on a project that was based at SLAC and really enjoyed living in the Bay Area. And then in 2005, a very interesting opportunity came up. People at SLAC were basically in the process of finishing building a new kind of telescope, a telescope that sees gamma rays. And they needed some people with particular expertise on essentially particle physics-y kind of things. And I'll talk a little bit more about why that is in the course of the talk. And so it was an opportunity for me to kind of do a little bit of a career shift. And I jumped at it. And a lot of the reason I jumped at it was because this was an entirely new kind of telescope. We hadn't really seen the sky in gamma rays up to that point. And so scientifically, the idea of just seeing the sky in a whole new way was extremely attractive. And so, given this opportunity, I just absolutely jumped at it. And I've been working on Fermi since then. At this point, I've sort of wound down on Fermi and started to move on to other projects. But Fermi's still up there. It's still taking data. It's still going strong after 12 years. And then my hobbies, basically they're Bay Area Burning Man related. I enjoy doing metal work and building art cars. On the right, you can see an art car that I built with a bunch of friends years ago. And then on the left and then on the right, you can see me showing off my flame-throwing guitar. That's probably why the SLAC PR people picked this particular title for this talk. But it's also because gamma rays see some of the basically the most violent events in the universe. Okay, so moving along, the first part of my talk is going to be about gamma rays. Since there's a bunch of astronomers here, I'm sure you're all familiar with the electromagnetic spectrum. Just a very brief reminder that gamma rays are really the most energetic kind of light there is. They're millions of times more energetic than a gamma ray is millions of times more energetic than a photon of visible light that we might be more familiar with. But again, I'm pretty sure that everybody here is familiar with the electromagnetic spectrum. When I came to SLAC, one of the very first things that somebody told me that's really stuck with me is that in astronomy, it's really important to look at something in as many different ways as possible. And when you're talking about the electromagnetic spectrum, to some extent, you're talking about looking at it in different colors. Or, if you go outside of the visible range, then looking at it in different bands. So you want to be able to see something with regular light, but then maybe with X-rays, maybe with gamma rays, because every new wavelength that you look at gives you a new part of the picture. And, if you're only looking at one color, I mean, just look around the room that you're in now and imagine only seeing the red things in the room. That would give you a very, very jaded view of the room. And it's only by looking and seeing the different colors that you can actually start to put things together and get a comprehensive image of what you're actually looking at. So, that's a little demo that I showed you there, how, if you're only seeing one color, you can kind of miss the whole. Now, scientifically, an example of this is the Milky Way. Again, I'm talking to a bunch of astronomers. I'm sure you're familiar with the Milky Way. Here's a really beautiful image. I think I got it from Astronomy Picture of the Day a while back. And, you can see the Milky Way, the band of stars that's going diagonally across this image. Now, this is a poster that a colleague and good friend of mine, Seth Diggle, made when he was working for NASA years ago. And what it shows is that band, the Milky Way, in 10 different wavelengths. At the top are the least energetic, the longest wavelengths, so radio. And at the bottom is gamma rays, and it's basically increasing energy as you go down. Each little slice shows basically the bands right along the plane of the Milky Way. And, there's the data are processed in different ways. There's different false color and so forth. But, in each slice, you can see that there's bright parts and there's dimmer parts. And then if you look more carefully, you can see that there's some sort of correlations and anti-correlations. Some of the bands seem to correlate really well with neighboring bands. Others of them don't. And in particular, I want to point out a couple things. If you look in the optical band, what you see are basically stars and clouds. You can see a lot of stars, you see bright spots, but you also see dark spots, along the plane of the Milky Way. Now, on the other hand, if you look in the near infrared, where the photons can make it through the clouds, you don't see the clouds anymore. You basically just see the stars. And in particular, you realize that the center of the galaxy, which is right in the center of this image, is really bright, whereas that's somewhat obscured when you're looking only in optical. If you go on to the mid-infrared wavelengths, then instead of actually seeing the stars, what you start to see is the clouds themselves that are shining. And looking basically between the optical and the mid-infrared kind of gives you this sense that the light that's being blocked in the optical, the dark bits, are actually shining. And so, basically what's happening is the light from behind those clouds is hitting the clouds, it's heating the clouds up, and then it's getting, because the clouds are hot, they're basically glowing in infrared wavelengths. If, on the other hand, you look in a different band, and in particular, you look at a band that's tuned to a very specific frequency or very specific wavelength where you can pick out particular transitions in molecules, then you can do something like you can map out where the hydrogen is in the galaxy, and you can make a really, really detailed map of where the hydrogen molecules live sort of in the plane of the galaxy. And if you look at a different wavelength where instead of being sensitive to transitions in the hydrogen molecules, you're sensitive to the atoms, then you can map out where the hydrogen that hasn't yet basically joined into molecules lives. Anyway, that little illustration was really to make the point that by looking at different wavelengths, you learn much, much more than you would in just a single wavelength. Okay, now I'm going to switch gears and talk a little bit about why we evolved to be sensitive to visible light. And I'm sure that, again, since I'm talking to a bunch of astronomers, I'm sure that, people are familiar with this and might have, some similar sorts of ideas. But I guess the first point is that the range of light where our eyes, basically the range of wavelengths where our eyes work, is rarely at the peak of the energy output of the sun. And so in some sense, that's where there's the most light bouncing around. That's where there's the most photons bouncing around. So if you were living on this planet and you wanted to evolve to basically be as efficient as possible, that's where you'd want to be able to see. And what I've plotted here is basically the spectrum of light from the sun and compared it to a black body spectrum, which is just the spectrum you get from sheer thermal radiation at a particular temperature. And you see that given the temperature of the sun, it's really peaking right in the middle of our visible energy range. The second reason that we have basically evolved to see at these wavelengths is the atmosphere is transparent at these wavelengths. This is a graph of how much light gets through the atmosphere as a function of wavelength. And you can see that in the visible band, almost all of the light gets through. And what this means is that you can see a long ways. You can see a good distance. You can see things that are far away. If you tried to evolve to see light at a different wavelength where the transmittance wasn't as good, everything would look foggy. It would look basically hazy, like it does when it's fog, when there's fog in the air and that's absorbing some of the light and not getting to you. So again, that's another reason where if you're living on the surface of the Earth, it makes a lot of sense to evolve to see optical light. And then the third reason is that photons of optical light carry just about enough energy to affect a molecular bond and change molecules. And that basically gives us a pathway to turn light into chemical signals that our brain can process and turn into information. All of that was basically telling you things that you're probably already familiar with about optical light. And the reason I did that is to draw a contrast to gamma rays. So here are some numbers about optical light. The surface of the sun is about 5,000 degrees. The wavelength of yellow sunlight is about half of a micrometer. By way of comparison, a human cell might be 10 to 30 micrometers across. And one photon of yellow light has about enough energy to transform a molecular bond. By way of comparison, if I were talking about gamma rays, those numbers would be, well, the temperature would be 2 trillion degrees Celsius. And the wavelength, rather than being, a fraction of a cell, it would be actually about the size of an atomic nucleus. And it carries enough energy not to transform a molecule, but basically to shatter the nucleus of an atom and just, splatter it all over the place and damage things around it, which is why gamma ray radiation can be dangerous. Okay, so then I'm going to switch gears again a little bit and talk a little bit about how gamma rays are produced. So thermal radiation, which you're familiar with, for example, for things that are glowing because they're hot, basically just depends on the temperature of the object. The hotter the thing is, the more radiation it gives off, and also the higher energy radiation it gives off. So a really hot blue star, really hot star would be blue. The sun is yellow. A dim older star would be red. Again, I'm sure everybody here is quite familiar with this. And a human would be, emitting in the far infrared rather than, in the middle of the optical energy band. Now, that's basically what sort of radiation you get just because of it's thermal radiation. It's the radiation you get because something's hot. If you look around in the universe and ask what's hot enough to make gamma rays, the answer is actually nothing. I've shown some sort of basically a chart of temperatures and energies, and the objects that have those temperatures. Our sun is a few thousand degrees. There are parts of objects like globular clusters or the active cores of galaxies where those temperatures can get up to 1,000,000 degrees or so, and can make X-rays. But nothing's hot enough to make gamma rays on its own. And this shouldn't be too surprising. Anything that, keep in mind that a single gamma ray has enough energy to dissociate a nucleus. So anything that was actually hot enough to be making gamma rays would essentially be in the process of blowing itself up and tearing itself apart. So you're not going to get a lot of things that are stable and just, glowing in gamma rays. So the question then becomes, how do you actually make gamma rays? Now, in a lab, the way you would make a gamma ray is you take a high energy charged particle, an electron or a proton or some particle that has a charge, and you'd accelerate it to really high energies, and you'd whack it into a target. The target could be an atom or a particle or a photon, just kind of anything that your high energy charged particle is going to interact with. And as part of that process of interaction, it's going to produce gamma rays, and it's probably going to make some other things as well. The point, though, is that the gamma rays are light. They basically travel to us, and so you can use them to do astronomy. So the question then is, how do you make gamma rays in astrophysical sources? What sort of things out there in the universe actually make gamma rays? And the sort of equation that I have here, the formula for making gamma rays, is that you need some sort of energy source. You need basically something to be dumping energy into its environment. And then on top of that, you need some way to accelerate particles. And then you need to run those particles into something. You need to have a bunch of photons around your energy source, or you need to have a bunch of particles. You basically need something to crash those accelerated particles into in order to make gamma rays. And then you need to be doing all of this somewhere where the gamma rays can then escape and make it out to you so that you can see them. So you have to worry about the foreground, what's between you and the place the gamma rays are being made. And if you get those things right, if you've got an energy source and particle acceleration, and you make the gamma rays and it's happening somewhere that you can see, then you can observe them. What we're talking about in terms of energy sources, basically the three main sorts of energy sources we're talking about are explosions, accretion, which is where a lot of material is basically getting sucked into a gravitational potential, a gravitational well, and it's getting squeezed as it's getting sucked in and heated up. And then some of it basically comes jetting out in the plane, perpendicular to the plane it's getting squeezed in. And you can see that in the middle image here. And then rotating fields, they can act like a big, rotating fields can act like a big motor, and they can accelerate particles up to very, very, very high energies. And then once you've accelerated the particles, there's a lot of different ways you can then make gamma rays. Did somebody have a question? Or okay. And I'm not going to go through all of these different ways. I'm just going to point out that once you've got the accelerated particles, they're pretty likely to run into something, and you're pretty likely to get some gamma rays out. Exactly how many and so forth, depends a little bit on the environment where you've accelerated the gamma rays. But having particles that are accelerated to really high energies and stuff is generally enough to get you some gamma rays. So to some extent, what you're doing when you're looking at the sky in gamma rays is you're basically asking where there are these really dramatic energy sources that can provide enough energy to accelerate particles up to really, really high energies. So then what I'm going to do now is talk a little bit about how you actually look at the sky in gamma rays. And so I'm going to talk about the telescope that I've been working on. The first point is just how you actually detect gamma rays. And this slide here is a slide I had a lot of fun making, where what I'm showing is basically telescopes across the entire electromagnetic spectrum. Starting in the bottom left are radio telescopes, and then sort of going counterclockwise, I go up in energies until I come to very, very high energy gamma ray telescopes. And Fermi is living over here, the third from the end. There's an old Galilean optical telescope in the middle, and I just want to spend a few minutes pointing out a few things about this slide. The first is that these telescopes all look really different from each other. A lot of them look like big tubes, but then there's some that don't. There's some dishes in there, there's some antennas. Fermi kind of stands out a little bit because it's just this big dumb cube in space, whereas a lot of them other ones look more like you might expect the telescope to look like. To my mind, some of the X-ray telescopes looks like some sort of crazy space cannon or something. And then the second point that I wanted to make is that some of these telescopes are in space and some of them are on the ground. And that comes back to the fact that in some wavelengths, the electromagnetic radiation can't make it through the atmosphere. And so if we want to do astronomy in those wavelengths, we have to go to space. So moving along, to observe gamma rays, you just can't use lenses and mirrors. They're not bent by, gamma rays are not bent by lenses and they're not reflected by mirrors. So doing something like you would do for an optical telescope just is not going to work. What you have to do instead is basically do particle physics. And what I'm showing on this slide is an old bubble chamber image from an old particle physics experiment, probably in the 50s or maybe even the 40s, where they shot a bunch of gamma rays at this particle physics detector. And what happened here is there was a gamma ray that was coming in from the left of the image, and right at the sort of left edge of this photograph, it interacted with something, and the gamma ray turned into two particles. It turned into an electron, but it also turned into the antiparticle of an electron, a particle called a positron. And then the way this experiment was set up, there was a magnetic field that made those two particles bend. And because the two particles have opposite electrical charges, they bent away from each other. And so you get this sort of V-shaped topology in this event. And if you look at the event, you can really quickly figure out where the gamma ray must have come from. These two things are moving from the left of the image off to the right of the image. So the particle must have come over from the left of the image. And so right there, what we've done is we basically measured the direction that one gamma ray is actually moving in. And so keeping in mind that gamma rays, basically in the atmosphere, what'll happen is a gamma ray will come in, it'll have this interaction, but then the electron and the positron will interact. And what you'll end up with is you'll end up with a whole shower of interactions. And sort of trying to figure out where the original gamma ray came from, it would be incredibly difficult by the time any of these things make it to the ground. So again, what you have to do is you have to go up into space. So the solution to these two problems is, well, first of all, you're going to need a particle detector. And second of all, you're going to need a rocket. You're going to need to put this thing in space. So basically, the Fermi Telescope is a particle physics detector in space. And that's why I got to work on it. I had expertise with particle physics detectors. And so, that's why the team wanted me to be working on it. And also, that's why it's so different from many other kinds of telescopes out there. So this is a picture of the whole observatory. So it's the Fermi Telescope, and it's also another instrument. And then it's the spacecraft that the two things are attached to. You can see the solar panels are folded up against the sides of the spacecraft. The telescope that I've worked primarily with is called the Large Area Telescope, and it's just this big cube that's covered in sort of silver protective foil up at the top. And another thing I want to point out is these are large teams that are working on these instruments. The Fermi team had about 400 members. The team for the other instrument, the gamma ray burst monitor, had about 40 members. So there's really a lot of scientists that it takes to get these things to work. So once we finished building the instruments and attaching to the spacecraft, they were shipped down to Florida and put on top of a rocket. You can see a picture of the whole assembly sort of on the rocket fairing, getting ready for launch. And then a picture of the launch. So at this point, and for most of the rest of the talk, I'm actually going to have a lot of animations. Again, these animations are all complements of the visualization group at NASA. And this animation, what it shows is basically how the Fermi instrument detects a gamma ray. So I'm going to go ahead and play the animation. And so the Fermi instrument, that big block, is actually a stack of silicon detectors that are basically stacked up into a tower. And what happens is when a gamma ray comes in, I'm going to just back that up just a tiny little bit. When a gamma ray comes in, that's your gamma ray there. And I'm actually going to take this moment to point out that one thing that the NASA visualization group that does is really neat is they always try and use the same colors for things. So gamma rays are always purple. So in all of the animations that you're going to see, purple stuff is typically the gamma rays. So the gamma ray comes in, it interacts with the detector, and it turns into an electron and a positron. And as those move through the detector, they leave signals in this sort of stack of silicon wafers. What we then do is we backtrace those signals and we figure out where the gamma ray came from. And so once we've done that, it's like with that old bubble chamber photograph that I showed you, we have the knowledge of where one gamma ray came from. Now that's just one gamma ray. That's a kind of slow way to do astronomy. It's kind of like pointillist painting. You know, you basically at this point, you can put one dot on your map of the sky. Now the way that this works is this Fermi telescope is in orbit, and I want to back up here a little bit and point out that it doesn't matter too much what direction the gamma ray is coming in. As long as it interacts, we can figure out what direction it came from. So unlike a lot of telescopes where you're focusing the light, in this telescope, basically, as long as the gamma ray comes in and interacts, you can see it and you can figure out what direction it came in. And that means that you have a huge field of view. You can see out to about 70 degrees away from the axis of the telescope. So at any one time, you're collecting gamma rays from a very, very large part of the sky. So what you do then is you basically just let the telescope run, you collect the gamma rays, you figure out what direction they came from, and you project them onto a map of the sky. You don't get that many gamma rays at any given time. So in a minute, you might get a dozen or so gamma rays. And what I've done is I've plotted them on a map of the sky, but you barely see anything. You see a few dots here. Again, this is just the beginning of a pointillist image. After an hour, you start to have actually a reasonable amount of counts, and you start to see that there's gamma rays. This particular map of the sky, the projection that I've used, it projects the whole sky onto an oval, and it puts the plane of the galaxy right in the middle of the oval. This will become more clear as I add more photons here. But anyway, after an hour, you have maybe hundreds of gamma rays. After a day, you're talking about maybe tens of thousands of gamma rays mapped across the whole sky. And at this point, you can really start to see the plane of the galaxy very clearly, and you can start to see individual bright sources. There's one here, there's another one there, and there's a few sources sort of more away from the plane of the galaxy. After a week, the sky sort of starts to come into focus. And then after a month and a year, you really start to have a lot of statistics. And after 10 years or so, you have almost 1 billion photons that you've collected, and you have a really detailed map of the sky. Again, this projection is showing the whole sky, and it's projected so that the galactic plane is along the equator of the projection. So that bright band right along the middle of it is basically our galaxy and sources in the galaxy. And then as you move away from that, you're basically looking away from the plane of the disk of our galaxy. Once we have that map of the sky, what we do is we basically start to analyze it scientifically, and to do that, we decompose it. The first thing that we do is we talk to our friends that have data from other wavelengths, and in particular from infrared and radio and microwave, where what they've actually done is they've traced out where all the dust in the galaxy, all the dust and gas in the galaxy are. And this is what the maps of dust and gas in the galaxy look like. And you can see that that looks a lot like sort of the map of the sky. There's a lot of the same structures. So right away, what you're seeing there is that most of the gamma rays that we see are coming from places where there's dust and gas. It's not so much that the dust and the gas is emitting the gamma rays. It's that there's just high energy particles that are zipping around our galaxy, and every so often they'll run into, you know, a little bit of dust or run into some gas and emit a gamma ray. And so the first thing that we're doing is we're basically tracing out where all the mass in our galaxy is, or all the matter, all the stuff in our galaxy is. As we sort of decompose the sky, the second thing that we see is a bunch of sources. All of these sources look a little bit blurred out, and that's basically the instrument that you're seeing. When we try and estimate the direction that the gamma ray is in, we do a pretty good job, but we don't get it quite perfect. And you know, this amount of blurring it's huge by the standards of what you're familiar with for optical astronomy. It's about, you know, maybe a half a degree or so. So, you know, if you're seeing on an optical telescope or half a degree, I mean, you just go home. You wouldn't even bother. But with gamma rays, that's about how well we can do. But fortunately, there's only a few thousand sources that we can detect in the sky, just because there's not that many huge explosions that give off enough gamma rays for us to see them all. So we can basically resolve the individual sources. You know, if you had the billions of sources that you can see with an optical telescope, obviously everything would be blurred together. But here, you know, obviously we're looking at thousands of sources in the gamma ray sky. You'll notice that a lot of them live in the plane of the galaxy. These are almost certainly sources that are in our galaxy. But then you'll notice that there's an isotropic component. There's a lot of things that live sort of outside of the plane of our galaxy, and it's pretty smooth. It's not like there's more towards the middle and less towards the edges. It's a pretty smooth sort of distribution of sources. And so that suggests that a lot of these things are actually outside of our own galaxy. And then the last thing is once you sort of accounted for all the sources that you can see, and you've accounted for all of the dust and gas in our galaxy, there's still a dim background of other gamma rays. And, you know, there's a question as to what that is. Is that just sources that we haven't really detected yet, or is it something else? But that's basically how we decompose the sky, whether the sort of three parts of the sky that we look at when we analyze our data. Okay, so now I'm going to shift gears, and I'm going to talk a little bit about the science highlights, sort of the things that we've seen with the Fermi Telescope. And I'm going to start with the most nearby things, and I'm going to move my way outwards. And again, this is going to be a lot of animations, courtesy of the NASA Visualization Group. So the first source that was really kind of surprising for us is actually gamma rays coming from the Earth. These basically travel about 1 millisecond to get to our instrument. And they're not actually so much coming from the Earth, they're actually coming from thunderstorms. And what this visualization is showing is a lightning strike in a thunderstorm that's basically shooting millions of electrons up into the atmosphere, up into higher layers of the atmosphere. And as these electrons move up through the atmosphere, what will happen from time to time is they will come near some particle in the atmosphere and they'll emit a gamma ray. And then that gamma ray can you know, interact with something else, make another electron and positron. And then those can interact with something and make more gamma rays. And so you get this whole sort of shower process. And what you see there is basically from this thunderstorm at the bottom, you see gamma rays kind of going out in all directions. It turns out that the electrons and the positrons, basically what they do is they get bent by the Earth's magnetic field and they spiral along lines of the Earth's magnetic field. And interestingly, what this means is sometimes our telescope basically sees a flash of gamma rays when we're above a thunderstorm. But every so often, we actually see a flash of particles hit the telescope when we're nowhere near a thunderstorm. And what's happened is those electrons and positrons that are traveling along the Earth's magnetic field hit our instrument and just light it up for like, a 1,000th of a second. And it's just this incredibly bright flash. And basically, we can't really use that data for astronomy. We just throw it out. But what we do is we get in touch with our Earth science colleagues, and we tell them that this happened, and we map these things out. And this whole process was really a surprise to everybody. People hadn't observed this sort of thing before, and so it was something just completely new. Moving along, the next closest source of gamma rays that I'm going to talk about are gamma rays coming from the sun, so about 8 minutes light travel time. And to illustrate this, I have an animation where I'm showing basically half of the sky. This is a different projection than what I was using before. And this is basically just, the way this is done is all the gamma rays for one day at a time were plotted together to make a movie. And what you can see, let me back up here. What you can see is that the gamma ray sky, things are blinking on and off. Things are variable. Some of these sources that we see, they flare up, they get dim again. That's just the nature of the sources. It's the nature of the fact that the processes that make gamma rays aren't something steadily glowing, but involve explosions and releases of energy. On top of all of that, you can see one source moving across the sky, and that's the sun. Now, I'm going to play this animation one more time, and just to show you that the sun is not the brightest thing in the sky in gamma rays at all. In fact, some days we can barely even detect it. So we've got this amazing telescope that can sometimes not even quite see the sun. But on other days, the sun can get tremendously bright. And on the days when the sun is really bright, it's basically when there's solar activity, when there's solar flares. And what happens, what basically causes solar flares, is the magnetic field of the sun recombining. That can release a huge amount of energy, and that can accelerate particles and make gamma rays. And there was one solar flare in particular, which I'm going to basically back up here, where this is what the sky looked like one day. And then when I play just a little bit, the very next day, there was just this tremendously bright solar flare. Basically, the size of that isn't actually the size of the sun. It's the resolution of the telescope. But what we saw is we saw literally millions of gamma rays coming from the place in the sky where the sun happened to be. So this was very exciting. Now, one thing that actually was interesting about that is when we talked to our colleagues who study the sun, and in particular, some missions that are basically looking at the far side of the sun, what we realized is that this particular solar flare actually happened on the far side of the sun. These two images are basically images of a movie of the near side of the sun and a movie of the far side of the sun. The far side of the sun is on the left. And so this solar flare happened on the far side of the sun. So what we weren't actually seeing was the solar flare itself necessarily. But what we believe happened is that all of the particles that got excited when the solar flare happened, they basically traveled along the sun's magnetic field lines, and they basically crashed back into the sun and made a huge bright splash of gamma rays. And so that's what we actually saw, which is why we were able to see this thing, even though it actually happened on the particle acceleration happened on the far side of the sun, but the gamma ray emission happened on the near side of the sun. Okay. Again, I'm going to basically move out again with our tour here, and I'm going to talk about sort of more astrophysical sources in our own galaxy. Remember when I showed you that map of sources in the galaxy, there was a lot of them that were in the plane of the galaxy. Almost all of these are pulsars. What a pulsar is it's basically the leftover remnant of a burned out star. It's a neutron star that's rotating extremely quickly. Typically, the pulsar's rotation period might be about a second or so. So this is something that has the mass of the sun, and it's spinning on its axis every second. This animation is basically showing the magnetic field lines associated with a pulsar, associated with this really high rate of spin. And the idea is that particles can get accelerated along these field lines and can produce gamma rays. Now, this is what our conception of a pulsar was when we started the Fermi mission. But once we started taking data, we actually realized it was wrong. And the point here is that if you look at this, you see where the gamma rays are. they're basically along the poles that this thing is rotating about. They're where all the field lines sort of bunch up at the poles of this object. And it turns out that's also where the emission in other wavelengths. You typically can see pulsars very brightly if you have a radio telescope. But once we took the data and we started talking to our colleagues who do radio astronomy, we noticed that there wasn't a lot of correlation between what they were seeing of the pulsars and what we were seeing of them. And so what this is suggesting is that the place where the gamma rays are being emitted isn't actually the same place where the radio waves are being emitted, but is actually somewhere different. And so the new updated model is that the radio emission is coming along the poles, but the gamma ray emission is actually coming sort of along those field lines. And in short, the reason that we think that is because there's a lot of pulsars that we see in radio, but we don't see in gamma rays. And there's a lot of pulsars that we see in gamma rays, but don't see in radio. There's just not that much correlation between the two different wavelengths. So that really tells us that the emission regions in the two wavelengths aren't the same. And now I'm gonna change gears again, and I'm gonna talk about more gamma rays from our galaxy, but in this case, it's from the diffuse emission in the galaxy. It's basically gamma rays from high energy particles that are moving around our galaxy and are interacting with things and giving off gamma rays. So this here is a map of what the Fermi sky looks like. Now, when we started analyzing this map, we did some things. We smoothed the data, and we did some data analysis to it. And then particularly when, sorry, I apologize for that. When we got to the point of subtracting off the emission that we believe came from, the dust and the gas that we know about. Once we did that, what we saw is that there was these big structures that we couldn't account for. So at this point, what we've done in this map is we've subtracted off, the emission, the gamma rays that we expect to see because of where we know all the dust and the gas in the galaxy is. And you can see right away that there's these big sort of remnant structures in the sky. And you notice also that they're centered around they're sort of pointing at the center of the galaxy. And they're huge. They're very, very large in a map of the whole sky. Given that they're pointing at the center of the galaxy, and given that we know the center of the galaxy is about 25,000 light years away, this is sort of an artist's conception of what that looks like. There's just these gigantic lobes extending above and below the plane of the galaxy of regions that are giving off gamma rays. To be able to give off gamma rays, there have to be a lot of high energy particles moving around in those regions, and they have to be interacting with things. We honestly still to this day don't know exactly what kind of high energy particles they are, and we don't know exactly what they're interacting with. This is still a big mystery. Clearly there's something there, but at this point we're still not 100% sure what it is. Anyway, this is a sort of static artist conception of this, and just to give you the scale, this thing is taking up a huge fraction of the sky, and the size of these bubbles is almost 50,000 light years across. So these are really very, very, very large structures. Okay, moving along. So I've talked about gamma rays from our own galaxy. At this point, I'm going to talk about gamma rays from beyond our galaxy. And I just want to remind you, when I showed that map of the sky, there were many, many sources that were sort of scattered across the whole sky. And we believe most of those to be extragalactic sources. And in fact, almost all of them, what we believe they are is objects called blazars, which a blazar is what happens when you have an active galaxy, which an active galaxy is when the black hole at the core of the galaxy is still actively sucking up a lot of material and basically burning very brightly. And it's as the material is trying to get sucked into the core of the galaxy, it's getting squeezed. This accretion disk is getting squeezed. And what you get is you get these really powerful jets of particles that are coming out in the plane perpendicular to the direction everything gets squeezed in, almost sort of like lasers. And what a blazar is it's when that jet points right at us. So, depending on exactly the direction that beam is pointing at, if it's not pointed quite at us, unless we're relatively nearby, this will just look like just any other galaxy. But if that beam is pointed right at us, it becomes tremendously bright. And these are some of the most distant objects that we can observe. And we can observe these things out to billions of light years away. And so one advantage that Fermi has is because it sees in gamma rays, and it's relatively hard to make gamma rays. Fermi is just a blazar detection machine. If we see something extragalactic, that's not in the plane of the galaxy in gamma rays, there's a very, very good chance it's a blazar. There's maybe a few dozen things that aren't blazars outside of our galaxy, but almost everything else is a blazar. And so that's very helpful because it confirms that it's a blazar, and it lets our colleagues who have telescopes that can see in other wavelengths, it lets them sort of look at it and follow up on it and so forth. Now, another thing that we can do with blazars is kind of one of my favorite things that Fermi did, which is basically measuring how much starlight there is in the universe. So I'm going to play another animation. This is the blazar here. And as you look, and basically this is what's happening in the jet. There's some gamma rays, and they're trying to travel to us. But to travel to us, they have to travel across billions of light years of distance. And in those billions of light years, there's some starlight floating around. And gamma rays carry so much energy that a gamma ray basically running into a photon of starlight every so often actually has enough energy to produce particles, to turn the gamma ray into an electron and a positron. If that happens, we won't see that particular gamma ray. That gamma ray won't make it to us. And what this means is that if something is really far away, the highest energy gamma rays from that object might not make it to us. And the further away it is, the more likely this is to happen. And also, it turns out the high energy gamma rays, the more likely this is to happen. And so what this allowed some colleagues of ours to do is basically to study the spectrum of blazars as a function of how far away these things are. They basically divided the blazars into groups of ones that were relatively nearby, which is only 2.5 billion light years away, ones that are a bit further away, and ones that are really quite distant. And what they noticed is that what they measured is that the spectrum of the most distant blazars really cuts off at the highest energies. Basically, the gamma rays have been absorbed, and you're not seeing them. What this allows you to do is it allows you to measure how often this interaction is happening. And then what that allows you to do is it allows you to tell how much starlight's out there. And if you have a good model for how much starlight a particular star makes, it allows you to count how many stars there are in the universe. So the estimate that they came up with this is that there's about 1.4 stars per 100 billion cubic light years. So obviously, if you're in a galaxy, the rate of stars is much, much higher than that. But if you're, there's just basically huge, immense voids between the galaxies. And once you average all of that out, there's really just not that many stars. You have to go, basically billions of light years, to get, or within a cube of billions of light years, there'll only be one star or so, which is a really, really, to me, again, this is one of my favorite things that Fermi measured. Okay, up to this point, I've been talking entirely about sort of traditional astronomy, looking at the sky in gamma rays and basically how we learn things about comparing what we see in gamma rays to what people see in other wavelengths. But another thing that the Fermi Telescope has done that's really very exciting is it's played a very important role in what's called multi-messenger astronomy. And what that is when we're doing astronomy with particles that aren't part of the electromagnetic spectrum, but other kinds of particles. And part of the reason that the Fermi Telescope is able to do this is because it's really great at seeing the biggest, sort of most cataclysmic events and explosions out there. Now, one sort of measurement that got a lot of news in the last few years has been the measurement of gravity waves. What happens is when you have two stars that are very close to each other and rotating towards each other, eventually they'll merge, but as they come very, very close to merging, they're moving around so quickly that they send ripples in gravity, sort of ripples in the space-time, that we can actually observe here on Earth if we have a sensitive enough instrument. Now, I'm just going to back this up a little bit. These curves here are the artist's conception of the ripples that we're trying to observe. But want to point out something really important. Once these things actually merge, it's a tremendous explosion. And when this explosion happens, you basically get all kinds of electromagnetic radiation, but in particular, you get a lot of gamma rays coming out. And you get the gamma rays coming out really quickly. You basically get the gamma rays coming out within a few seconds of when the merger happened. And then you get X-rays and optical light and all different kinds of light. And again, the point here is that it's just about looking at the same object in as many different ways as possible. And so one really great thing is, the gamma rays, they're basically one of the first messengers to get to us from this event. So they tell us what's going on, really right after these two stars merged. Another kind of multi-messenger, astronomy, also was very prominent in the news recently, and it was a different kind of particle called a neutrino. Now, neutrinos are kind of similar to photons in that they don't have an electrical charge, but they're very different from photons in the sense that they almost never interact. Now, this is an artist's conception of an active galaxy, and you can see the jet in the active galaxy, this beam that's coming out here. And an interesting thing is that the processes that make the gamma rays and the processes that make neutrinos are very similar. And it turns out that we pretty much expect to see the same number of gamma rays and neutrinos. But the gamma rays are really easy to measure. The neutrinos, on the other hand, are incredibly difficult to measure, and we've only been able to observe neutrinos from outer space in the last few years. There is an observatory that's actually buried in the Antarctic ice, where what they've done is they've put a lot of particle detectors miles deep in the ice. And what happens is, as a neutrino can come in, maybe 1 in a million or even less will interact with the ice. And as it travels through the ice, it'll give off light. And their detectors can basically observe this. And they can basically trace the particle as it goes through this array of detectors they have so deep in the ice. And they can figure out the neutrino, the direction the neutrino came from. Now, they've started to observe neutrinos. They've got, a few thousand neutrinos they've seen from the whole sky, and it's still not entirely clear where all of these neutrinos are coming from. But in one particular case, we got a very, very serendipitous discovery, which was that there was a source, a blazar, one of these beam sources, that was flaring in gamma rays. It was much brighter in gamma rays 1 week than it was typically. And during that same week, we observed a neutrino that pointed back to exactly that same part of the sky. And so, we calculated the chance probability, the chance that this is a coincidence, and it was very, very small. So in all likelihood, this particular neutrino came from the same mechanism that was making this blazar flare up in gamma rays. So again, this is an instance where, you learn much more by looking at something in two different ways than you learn by looking at it in a single way. So what that sort of means is that traditionally, if you're an astrophysicist rather than an astronomer, what you've been thinking about are photons and atoms and electrons and protons and the interactions between them. That basically tells you what things look like when you look at them in a telescope. But now that we have these multi-messengers, you also start to think about neutrinos. What makes neutrinos? How do they interact with, with the environment around them, and about gravity waves? And you basically have more ways of exploring the universe and more ways of exploring the sky. So at this point, I'm getting to the summary. It's been about 50 minutes. And so first off, Fermi's turned 12, and it's really dramatically changed the way that we understand extreme phenomena in the universe. Like most research telescopes, it's used for a lot of different things by a lot of different people. I probably don't have to explain that to this group. And again, some of the most exciting discoveries that we get with Fermi comes when we combine Fermi data with other telescopes. And again, this is just very common in modern science. The really great discoveries come when you put together different puzzle pieces from different places. So thank you, and I'd be happy to take questions. Would you like me to stop sharing the screen or leave it up?
You could leave it. So I had one question at first, but then later in the lecture, you kind of answered it. I was concerned that by taking this 12-year picture over multiple years, you will miss individual events. But then I saw that you still look at individual days.
Absolutely, absolutely. We yeah, one of the big things that Fermi does is provide what we call transient alerts. And keep in mind that at any given time we can see a huge fraction of the sky, about 1/5 of the sky at any given instant. So if something happens in that part of the sky, if there's a very bright cataclysmic event, typically things like gamma ray bursts, we know almost right away. And so one thing that we do is we provide alerts for other telescopes to follow up. So we put out, an astronomer's telegram saying we detected a gamma ray burst, in this location, and people will follow up on that. Actually, for gamma ray bursts, it's not an astronomer's telegram. There's a different network that you basically put out the coordinates and encourage people to follow up on those. So yeah, transient alerts are a really big part of what we do.
So there's a question in the chat. What is the briefest event Fermi can detect? How fast is a gamma ray burst?
So there's people that the taxonomy is people talk about short gamma ray bursts and long ones. Short gamma ray bursts can be less than a second. The way Fermi works, remember, we're detecting individual photons. If two photons come in within about a microsecond of each other, it really complicates things, and we have a harder time basically disentangling them and deciding where the event is. But if they come in more than a few microseconds apart, we detect them as individual events. So what a gamma ray burst could look like to Fermi is sort of over the course of a few, like a second or so, we might see dozens of events coming from the same direction in the sky. The individual events, we're time tagging down to, much less than a microsecond, probably a few hundred nanoseconds. But we can't, if 50 events came in all at exactly the same time, we wouldn't really be able to make much sense of it. We'd just be like, oh, wow, what was that? So it's this weird sort of thing where, we would have known something happened, but we would have gotten, it just kind of overwhelmed our instrument. We would have gotten confused about it. But certainly we've seen gamma ray bursts that are, shorter than a second, and we've seen many individual photons from those gamma ray bursts. Does that answer your question? I can't see the chat window, so.
Okay. No problem.
Someone in
Yeah,
the chat is typing. I can read the question if you want.
Oh, I've got it, actually.
So yeah, that was satisfactory answer. Thanks. Anybody else? You can unmute yourself and talk away. Now's the time to ask any doubts and.
Yeah, so you said a gamma ray has enough energy to disassemble an atomic nucleus.
Mm-hmm.
Could you hypothetically use a gamma ray to do nuclear fission?
That's exactly what nuclear fission is.
Oh, okay. Right.
So yeah, I mean, there are other things that break, like,
Yeah.
But in part of what happens in a chain reaction is like gamma rays hitting other nuclei and breaking them apart. There are other things that do it too, neutrons and so forth. But yeah, that's exactly what it is.
All right, thank you.
Are there any theories on what those big regions above and below our galaxy are?
There are a great many theories.
Okay.
Yeah, the thing that's really striking about them is that they have very sharp edges. It's kind of hard to make something that has a sharp edge when you're talking about sort of high energy particles that are just kind of flowing around the galaxy and running into things and giving off gamma rays. You need something to confine them there. So you know why there's that sharp edge is basically the thing that you have to explain if you want to explain why, you know, what those bubbles are. Does that make sense?
Yeah.
I see
There were way too many theories to go over them now. Yeah.
Yeah.
It's,
Yeah. Also, there's no really compelling evidence that favors one theory over a different one. You know, some examples of the theories are that our galaxy used to be active and basically was pumping out, you know, there was a lot more stuff going on in the center of the galaxy, and we pumped out tons and tons and tons of really high energy particles. And then we turned off. And so what we're seeing is the residue from those high energy particles. But for a variety of reasons, there's, you know, it has to be more than that. That theory, it's just by itself doesn't quite account for anything.
Okay.
I see
So
there's
another question on the chat, if you
Yeah.
don't mind. When gamma
So when
rays enter atmosphere.
Yeah, that's exactly what happens actually. When a gamma ray hits the atmosphere, you typically don't talk about an interaction. You talk about an electromagnetic shower, which is basically a chain reaction. One gamma ray makes an electron and a positron. The electron and the positron interact with things and make more gamma rays, which make more electrons and positrons. Interestingly enough, that fact is actually used as the technique if you want to go to energies that are even higher than what Fermi detects. Fermi,
Hold on.
Fermi can detect basically up about 1 trillion electron volts. Fermi isn't big, those gamma rays are so rare that we just don't see very many of them anymore. But if you had, what people do at the highest energies is they basically build an array of telescopes that look at the atmosphere and digitize the data really, really quickly and look for incredibly short flashes. And they image those flashes, and those flashes correspond to the electromagnetic shower that you might have gotten from one extremely high energy gamma ray. And that's how you do astronomy at the very, very highest energies. I apologize if that explanation is not entirely clear. I can either follow up on that, or I can answer the question in the chat about how often Fermi sends data. Okay, I'll go ahead and answer the question in the chat. So basically, there's two ways we send data. We've got sort of a slow data stream where we're constantly sending a little bit of data, and we use that for sending instantaneous alerts, but it's a really slow data stream. We can't get much down on that. We can get alerts, and so we do have processes that run on the spacecraft that you know, identify when something like a gamma ray burst happened and generate the alert so that we can get it out right away. But the bulk of our data gets stored on the instrument for up to a day or two, usually much less than that. And we basically use a NASA communications web to get that data down 5 or 6 times a day. So typically we're updating, you know, we're updating our maps, and we're looking at the whole, you know, the sky data every 4 to 6 hours. And, you know, the data come down, and then we typically process the data within an hour or two. And so, you know, within half a day of when the data were taken, you know, we've basically updated our maps of the sky. Can you detect magnetars? Magnetars, the bottom end of the Fermi energy range is effectively about 100 million electron volts. And magnetars tend to emit a little bit below that. The other instrument that I didn't really talk about on Fermi, it's a monitor for gamma ray bursts. They do detect magnetars, but the large telescope that I work on, we typically don't. In fact, I don't think we've detected any. No, we're not. No, the only thing we see are these lightning strikes. Well, the other thing that we do see is what's called the albedo and the Earth limb, and what that is high energy particles crashing into the Earth and giving off gamma rays, and those scattering back up out of the atmosphere and and hitting Fermi. Actually, one of the brightest things in the sky is the edge of the Earth, the so-called Earth limb for us. What basically happens there is that these millions of cosmic rays that are sort of zipping around, they sort of graze the Earth's atmosphere, make some gamma rays, and then we see that. And we actually have to remove those from our data analysis because they're not, they're coming from the Earth, they're not coming from the sky, and it's just tremendously bright. So typically when we analyze the data, we basically throw away all the data that's within about 10 degrees of the Earth. And so typically, we point away from the Earth, and we try not to point too close to the edge of the Earth because that data we would have to throw away. Does that answer your question? Well, not on a large scale. These blazars, these extragalactic sources that are so distant, they're all over the sky. They're what we say is they're isotropically distributed. There's a few patches where there might be like a little. You might be able to draw like a little 10-degree circle and not happen to have any blazars in there. But that's just sort of random statistics. Pretty much, I mean, in fact, if you look at this map that's here on the thank you screen, you can't see any region that really stands out as dark. And even like, okay, I might take this region here, they're not really, you don't see a lot of sources jumping out, but there's a little guy here, there's another guy there, there's another guy there. And you'd probably have a hard time. The question is, are there parts of the sky that are dark, lacking gamma rays? And what I'm saying is that there's, you could probably draw maybe a 5 or 10 degree circle and not have any real sources in there. You'd still have some background gamma rays and so forth. But given that we've detected about 5,000 sources in the sky and there's about 40,000 square degrees in the sky, that's just kind of statistical fluctuations. There's nothing where it's like, oh my God, there's this giant hole of gamma rays at any part of the sky. Hey. Well, I mean, NASA is an incredibly conservative organization in the sense that they really hate failure. So they're not going to let you fly something unless they're 100% sure it's going to work. So when it was launched, Fermi represented some pretty old school technology at the time. Now, it was old school technology that was adapted to space, which is very, very, very challenging. In terms of things like the electronics that are reading out the data and how finely segmented we can make the detectors and how good we can make all of that, we could certainly do better. But none of that's really a game changer. Our efficiency for detecting a gamma ray that hits the Fermi instrument is about 50%. So even if we got that up to 100%, we'd have twice as much data. But if you have twice as much data, you'd still have to run for 6 years to just get to the point where we are now. The kind of rule of thumb is that to really make a NASA mission be viable, to be worth the investment, you want to be doing about 10 times better than what you were doing before. So the idea there is that in 1 year, you can match somebody else's 10-year data set. And the only way we could do that would be by making Fermi much, much, much larger. The other way we could do it would be by making the spatial resolution a lot better so that these little, these sources were less blurry. But there's a whole separate raft of challenges that are associated with that. So at this point, and the other thing is that NASA tends not to turn things off while they're still working. I mean, Hubble's been up for forever. So at this point, I think basically NASA's policy is just to keep Fermi up there, keep their fingers crossed that it keeps working. We say a lot of times when we talk about Fermi that there are no consumables. There's nothing that's going to run out. There's no fuel, there's no coolant or anything like that. it will eventually stop working. Something will go wrong and it'll stop working. But for 12 years now, we've been able to run the thing very, very close to its nominal configuration. A place where we can do better is at the low end of the Fermi energy range. Below about 100 million electron volts, it becomes really hard for us to figure out what happened. And there are other technologies that could work better down there. And so the successor mission to Fermi is almost certainly going to be in that energy range.
Do we have any more questions?
Well, yeah, it's just not on the presentation.
Go ahead.
So I'm a high school student graduating this year, and I was just wondering how I go about getting a job like in the field that you did. So like in labs where you send instruments into space, because I'm really interested in astronomy and astrophysics.
There's a lot of different paths. First off, I mean, almost everybody that I work with, but not everybody has a degree in physics or astronomy or computer science or engineering. Something that is relevant there.
Right.
It's not actually everybody. There are a few exceptions to that. But that's by far and away the easiest path.
Yeah.
The second point is most of the people that are doing the sort of stuff that I'm doing, which is sort of looking at the data and helping build the instruments, actually have PhDs.
Right.
You went to grad school, you learned the particulars of, either a particular kind of astronomy or a particular kind of instrument. But I work with a great many people that don't have PhDs. People that help write the software that control the spacecraft. Some people that help write the software that analyze the data and so forth. A lot of them have engineering degrees and so forth. Then on top of that, most people did a lot of sort of internships, and if they didn't go to grad school, then they did internships and things like that in this particular field.
Right.
I think the obvious thing to do for you if you're a high school student would be go to college and pick a major: physics, astronomy, engineering, whatever is the most interesting for you, and just keep in mind, well, I want to work on space stuff, and so just talk to your advisors about that, find opportunities there. And I guess the last thing is that the thing that really stands out about my colleagues and the ones that stay in academia is, more than anything else, it's the ones that really wanted to do it, that really, really wanted to stay in academia, the ones that found a way to make it work. Sometimes that's really difficult. We actually had a career development panel that I organized not so long ago, where some people, some people, including some people kind of senior in the field, came and talked about, how they got to be where they are. And every single one of them talked about, there was a period where they were applying for jobs and just not getting any jobs. And it was discouraging. And, the thing that stands out from that is, well, they stuck with it, and they kept doing it until they did get a job. I hope that answers your question.
Yeah, thank you.
Eric, can you hear me? This is Linda.
Mm-hmm. Yes, I can.
Oh, I want to thank you so very, very much for giving this incredibly interesting talk. I'm glad it's recorded and the details can be over. I've written pages of notes while you were speaking, and I know other people did too. But it was very, very interesting, and I thank you for taking your time and effort to do it for us tonight.
Thank you very much for the invitation. It was really very fun.
Yeah, good. Thank you.
gotta go ahead and stop sharing my screen. And,
Well, everybody, thanks for coming to our lecture. And thank you for joining us one more time.
Yeah, thanks for organizing it. This was really nice.
Yeah, we're here to serve our members and the public. We enjoy listening to the talk ourselves. But yeah, the board thanks Linda for getting in touch with the speakers and lining them up month after month. We enjoy the subject as much as you do. So I hope you keep in mind the lectures that Linda outlined for the future, and I hope to see you again. Good night, everybody. Also, if you have any questions about the election or about being a member, I can stay on a little more.